My name is Aniket Koul, and today we'll be discussing the eighth problem from the CP-31 sheet by TLE Eliminators under the 1200 questions. I'll be moving to the CP-31 sheet, and we can see that we have a clickable link to our eighth problem, Dora and Search. So let's begin. Problem states as follows. As you know, the girl Dora is always looking for something. This time she was given a permutation and she wants to find such a subsegment of it that none of the elements at its ends is either the minimum or the maximum of the entire subsegment. More formally, you are asked to find the numbers L and R such that L and R lie between 1 and n and L is less than equal to R such that A of L is not the minimum of that subsegment AL to AR and A of L is also not the max of the subsegment AL to AR, and the same follows for A of R as well. A permutation of length n is an array consisting of n distinct integers from 1 to n in any order. For example, 2, 3, 1, 5, 4 is a permutation, but 1, 2, 2 is not a permutation because 2 occurs twice in this array. And 1, 3, 4 is also not a permutation because n equals to 3, but 4 is present in the array. Now you have to help Dora find such a subsegment or tell her that such a subsegment does not exist. Right. Now coming to the input format and constraints, the first line of the test file would contain a single digit t denoting the number of test cases, and t can go up till 10 power 4. Then for each test case, we'll have the first line as one integer that will denote the length of our permutation, and it can go up till 2 into 10 power 5. Then on the next line, we'll have n distinct integers a1 till an, where ai is between 1 and n, and these elements are forming a permutation. Now it is guaranteed that the sum of n overall test cases does not exceed 2 into 10 power 5. Right. Now we want to output -1 in the case if any subsegment does not exist, which follows a given condition. Otherwise, output the two indices L and R such that A of L to A of R satisfies all the conditions mentioned above. If there are several solutions, you can output any one of them. Great. So as we have read the problem statement, we can move on to understanding what the problem is actually saying. So according to the problem statement, we'll be given two things, n and let's say a. So n is an integer that denotes the size of the permutation. Size of the permutation, right? And a is that permutation, right? So if I would to recap what is actually a permutation, so if a is a permutation of let's say size n, then a must contain all values from 1 to n exactly once, right? And that can be in any order. So if it contains all values from 1 to n exactly once in any order, a will be called then a permutation of size n. Great. Now we are given these two things and we are asked to find a subsegment L to R such that the elements AL, AL plus 1, AL plus 2, so on till AR minus 1, AR. So this subsegment must follow few conditions. Now what are those conditions? The first condition is that A of L should not be the minimum of AL to AR, right? Similarly, A of L should not be the maximum of AL to AR. And this will apply for A of R as well. So A of R should not be minimum of AL till AR and should not also be the maximum of AL till AR. Now these are the four conditions we can say that must be followed by a subsegment defined by L and R, which are the starting and ending indices, for it to be called a good subsegment. Now we are asked to output this L and R in one based indexing. So one based indexing. And if there are multiple answers, we can output any one of them. And if in a case there is no possible answer, then we have to output -1. Right. So this is the problem statement. Now let's discuss a sample case to understand the problem better. So I'll be moving back to the question and let's pick up these two cases. Right. And I'll be pasting them here, moving anything that is not necessary. And I'll also increase the font size so it is better visible. Great. Now here this is N, this is A, this is N, this is A, because these two are two different test cases, right? This is the first test case, this is the second test case. Coming to the first test case where N is equals to 3 and A is 1, 2, 3. Now here let's say I take L to be 1 and R to be 3. Right, so this is L equals to 1, R equals to 3. Here if we see this subsegment, which is basically the whole array, A of L is 1, which is equal to the minimum of AL till AR. Also A of R equals to 3, which is equals to the maximum of AL till AR. So I can say that L equals to 1, R equals to 3 is not a possible answer. And in this case especially, take any L comma R which follows the condition that 1 less than equals to L less than equals to R less than equals to N, you will find that no possible pair of L comma R will form a good subsegment. So that leads to the conclusion that my answer would be -1 in this case. As you can see here in the question, in the sample cases, we see it is -1, right? Now, let's move on to the second case, this one. 4, 1, 2, oh, sorry. Size is 4 and 2, 1, 4, 3. If I choose here L equals to 1 and R equals to 4, right? So in this case, A of L equals to 2, A of R equals to 3, minimum of AL till AR is equals to 1 and maximum of AL till AR equals to 4. You can see AL is not equal to the maximum or minimum. AR is also not equal to maximum or minimum. So L equals to 1 and R equals to 4 is a possible answer. Therefore, I will output 1 comma 4, not the comma, but 1 and 4. And this would form a good subsegment. Great. Now, as we have discussed the sample cases as well, let's move on to discuss the expected time complexity. Now, in the question, it is given that sum of n overall test cases does not exceed 2 into n power 5. So, if there is no bound on sum of n overall test cases, then we would have to consider something of the form of t into f of n, where this is a function of n. But as we have a bound over sum of n overall test cases, so we don't need to consider t because that would be included here. So we can simply write it as O of some function of n. And now let's discuss how high can we go. And before that, we'll discuss our limit. So we know that on Codeforces, in 1 second, we can run about 10 power 8 elementary operations. And if we see our problem, we know that we have only 1 second time limit. So therefore, I want f of n to be such a function where the number of operations are less than 10 power 8. So if I consider O of n, that would lead to around 2 into 10 power 5 operations and that would run very comfortably. O of n log n, where this is base 2, would run in 2 into 10 power 5 into log base 2 of 2 into 10 power 5 would be around 20. It will be less than 20, but we can consider it just to be safe. And this value would be around 4 into 10 power 6 and this should also run pretty comfortably. But if I go O of n square, then this would be 4 into 10 power 10, and this won't run. So I know my bound is around n log n. So I want to find a solution which can run in this domain. Great. Now we have discussed the expected time complexity as well, and we can start discussing the solution. Right. So the biggest hint to this problem is that we are given A is a permutation. Right. Now let's think of the problem in this way. Let's say I have this array A where I have A1, A2, A3, so on till AN, where n is the size of the array, like mentioned in the question. Let's say initially my L and R were 1 and n, right, in one based indexing. Great. Now, what would be minimum of AL till AR? Will it be constant? Try to think of it. It will be, right? So this would be max. These two values have to be constant, right? Because as it is a permutation, the array will contain all numbers from 1 to n exactly once, right? So minimum of AL to AR would always be 1 and maximum of AL to AR would always be n when L equals to 1 and R equals to n. This is pretty straightforward, right? So if I start from this case, so I start from the case where L is equals to 1 and R equals to n, I know my minimum and maximum values of the subsegment, right? So quite simply, if AL is not equal to 1 and not equal to n, also if AR is not equal to 1 and not equal to n, I can simply say that here L is equals to 1 and R equals to n. So I can simply say that 1 and n form a good subsegment. So this is my possible answer. Right. This is pretty straightforward. Now I want to think of a case where this won't happen. Right. So let's say I had my A1, A2, so on till AN, and let's say my AN A1 was N, let's say. Right. So now if I consider L comma R as 1 comma N, then it won't be a good subsegment. Why? Because A of L, which is basically A of 1, is equals to N. So it is equals to max of the whole subsegment. Therefore, this won't be a good subsegment. Now, what should I do? Let's think of it. Right. So let's think of a case where we are fixing L. So I'm fixing my L equals to 1 and I'm moving my R. Okay. So I'm moving my R. Now try to think if A of L was N, and because A is a permutation, so you take any subsegment which starts at 1, or in this case L, because I'll be generalizing later. So any subsegment that starts at L where A of L is N, it will have its max element to be N. Try to think of this, right? Because my A is a permutation. So the maximum value that I can have in my array A should be N. So if A of L is itself N, then no matter what is R, the maximum will always be N. Correct? And this similar logic would also apply to if A of L was equals to 1. So if A of L was equals to 1, that means no matter what R is, the subsegment that I choose will have its minimum value to be equal to 1, right? So that means if A of L equals to N or A of L equals to 1, that means I have to move L. So I have to go to L plus 1, or that is equals to 2, right? Because there is no such case where fixing L would give me a solution. So I have to move L. And now think of it that could we extend the same logic to R as well? Because if A of R was equals to N, that means no matter what L is, the maximum value would still be N. So I have to move my R. Similarly, if A of R would be 1, then the minimum value, irrespective of what L is, would be 1. So again, I have to move my R. And in this case, what would I do is I would move R to R minus 1. That is, I would move it to N minus 1 in one base index. Right? So this much should be clear. This is for the starting case only. Now you might be thinking why I'm using L and R and not simply 1 and N, because now we'll be discussing that could we generalize this. So no matter of the value of L and R, is it possible that always following the condition that L goes to L plus 1 and R goes to R minus 1 will lead to a correct solution? Let's think of it. Right. Let's say currently my subsegment is starting at L and ending at R. And now I'm not restricting my values to be 1 and n respectively. Okay, so these two can be any two random values given the condition that 1 is less than equal to L, less than equal to R, and less than equal to N. So I'm not fixing those values. I am just following this condition, and under this condition, L and R can be anything. Now, can I say that if A of L is the minimum of A of L till A of R, or A of L is the maximum of A of L till A of R, then I will move L to L plus 1. Can this be a correct logic? Try to think of it. Try to think of it in this way if you're not able to visualize it. Let's say this is my L and this is my R. Now if L is equals to 1, obviously I can't move back because this is the start of my array. So I would have to move L plus 1. Right. So this case is clear. But let's think where L is not equal to 1, right? So I have some headroom to move backwards as well. But would I do it? Would it be feasible? Let's say I move to L minus 1, right? Now, if L minus 1 comma R would be a possible solution, let's say it was a possible solution, then wouldn't I have received it in the previous iteration itself? Because every time I'm moving inwards, so L is always increasing. L is going to L plus 1 and then going to L plus 2, so on. So if L minus 1 was giving me answer with R, then I would have received it in the previous iteration itself, because I'm always moving inwards and not outwards. For a specific case, let's say 2 comma 5 was giving me an answer in n equals to 5, right? So L equals to 2 and R equals to 5 was giving me a good subsegment, right? So if 1 comma 5 would have given me a good subsegment, I would not have reached this case itself, because I'm checking this case at first. Because this 1 comma 5 did not give me a good subsegment, that's why I moved to 2 comma 5. So moving back to 1 comma 5 would not make a lot of sense, right? So always I would keep moving forward in the right direction with L. And similarly extending this logic to R as well, that I would never go to R plus 1, right? Because if L and R plus 1 would give me a solution, I would have gotten it in the previous iteration itself, correct? So that's why I always go from L to L plus 1 and from R to R minus 1, basically narrowing my subsegment in each iteration. Initially it is 1 comma n, my L and R. Let's say A of 1 does not satisfy my condition. That means either A of 1 is equals to 1 or A of 1 equals to n. Then what would I do? I would check for 2 comma n, right? And let's say in 2 comma n, this R does not follow my condition. So A of n is either equal to 1 or A of n equals to n. So in this case, I would move my n to n minus 1. Similarly, basically what I would be doing is following this type of function, that if a of L is minimum of the subsegment or the maximum of the subsegment, then I would be moving to a of L plus 1. Or if a of R would be the minimum or the maximum of the current subsegment, then I would be moving to a of R minus 1. And this would continue until I find a subsegment which is actually good, which is following my all the conditions. And if in some case I don't reach that condition, then I would be outputting minus 1. And we can also discuss using our algorithm what would be the case that gives us minus 1. Okay, so let's think of a case. So 1 comma n is not satisfying, 2 and n is also not satisfying, 3 and n is also not satisfying, 4 and n is also not satisfying, so on till n minus 1 and n is also not satisfying. That means moving L does not work. Similarly, 1 comma n does not satisfy, 1 comma n minus 1 does not satisfy as condition, 1 comma n minus 2, so on till 1 comma 2 also does not satisfy. So if you try to think, this can only be possible if our permutation A is an identity permutation. That means A is basically 1, 2, 3, 4, so on till n. So if this is our array, then no matter what subsegment you choose, A of L would always be the minimum of a subsegment and A of R would always be the maximum of a subsegment. Right? So choose any L and R in this array and you will find that A of L would always be the minimum of the subsegment and A of R would always be the maximum of the subsegment. And because in all the steps where I was discussing anything, I was saying that if it is if this is true for L, then it would also be true for R, but just in reverse. So in this case, that is also possible. So if 1 till n is a minus 1 case, then n till 1 would also be a minus 1 case. Why? Because here any L would lead to A of L being the max value and any R would lead to A of R being the minimum value of that subsegment. That's why these two will not satisfy any subsegment and thus lead in minus 1. Right? But you don't need to hard code this because our algorithm will automatically take care of this. You just need to move L and R like just as said. And if L is greater than equal to R, then I would simply output minus 1. Because L equals to R is also minus 1 case. Because if the subsegment is of just size 1, then A of L is the minimum and the maximum, and A of R is also the minimum and the maximum. Right? So this is basically our whole approach. And we'd be using a two-pointer algorithm to achieve this because we'll have two pointers L and R, and we would be moving them according to some given conditions. Now, the only thing that remains is how to check if how to check basically if A of L is maximum or minimum of my subsegment and if A of R is the maximum or minimum of my subsegment. So how do I check this? I need to check this quick, right? Because if I check this in O of n, then as two pointer is itself O of n, that would lead to O of n square time complexity, which is not possible. So my two pointer takes O of n time. So I need something which runs in O of 1 or even O of log n is fine. So I need to find something that gives me the maximum and the minimum values in O of log n time. So how can I achieve this? It's pretty simple. Just use a set in C++ because it stores all the elements in sorted order. So the first value will give you the minimum value of the subsegment. The last value would give you the maximum value of the subsegment. And how to update the set? Just whenever you are moving L to L plus 1, remove A of L from the subsegment. Similarly, whenever you are moving from R to R minus 1, remove A of R from the subsegment and or the set, and it will be updated automatically. Right. And every erase operation takes log time. So at max we'll have n erases because the array itself is of size n. That's why it will have the time complexity O of n log n. Right. So I hope the explanation is clear, and now we can move on to the implementation part. So I'll be moving directly to the main function, and here I have taken the input for the number of test cases. Then for each test case, I would take in the input of n, which is the size of a permutation. Then here I would take in the input and store it in a vector named as array. So to take input, it takes O of n time for n sized array. Now I've initialized a set using my vector. So this format is pretty simple to write. So what it does is it creates a set with all the elements in my array ARR, right? So this would take O of n log n time because inserting one element takes log n time. So I'm inserting n elements in the set, so it will take n log n time. Great. Now these two I and j are basically the L and R that I discussed in the problem. These two are same, and I've started them with 0 and n minus 1. Why? Because in the question I need to output in one based indexing, but as we know that computers are 0 based indexed, so I would start instead of 1 and n, I would start at 0 and n minus 1 because 0 would be the first index of my array or my vector, and n minus 1 would be the last index of my vector. And simply using a two pointer approach, so while I is less than j, I am checking here that if array of I, which is basically if A of L is either the minimum or the maximum, and here I'm checking whether A of R is either the minimum or the maximum. And how am I doing this? So let's move on to the function first. So I'm passing the set by reference. So this will give me the updated set, and I'm passing the value as well. So value in our cases would be A of L and A of R. So I'm checking if the value is equal to the first element of the set. So that means the value is the minimum value in the set. So I will return true that yes, it is the minimum value in the set. And even if it is the last value, so dot r begin points to the last element in the set. So if it is equal to my value, then also I will return true because it will be my maximum value in the subsegment or the set. And if it is not, then I would simply return false. So this function would basically give me if the value val is either the minimum or the maximum value in my set. So this function is O of 1, you can say, because you are just accessing a pointer. Dot begin and dot r begin are functions which store the first and last value. So it is almost O of 1. So these function calls are O of 1, but here we are using the erase function in a set, and as we know, erase and insert operation in a set takes O of log n operations or O of log n time. Yes. So if A of L or basically array of I is my minimum or the maximum value, so I would erase array of I from my set and perform I plus plus. In the same way, if array of j or a of r is the minimum or the maximum value in my current subsegment, then I would erase that value a of array of j and I would move to j minus minus. Right, and in both cases I would continue. And if in a case that a of L is not the minimum or the maximum and a of R is not the minimum or the maximum, that means L to R subsegment is a possible answer. So I would break here, right? Because I have found a possible answer. Now outside of the while loop, I would just check if I is less than j. Because if I is less than j, that means I have found my answer or a possible subsegment. And if I is greater than equal to j, that means I have exhausted all my options, but still I have not found a possible answer. So if I is less than j, I would simply output I plus 1 and j plus 1, because I want to output in one based, but I and j, as I discussed here, are in zero based. Correct. And if I is greater than equal to j, which is the else condition, then as I said, I have exhausted all my options. So I would simply output -1. Great. So coming to the while loop time complexity, this would be n log n of n log n. Why? Because two pointer takes O of n operations, and in each operation we might do a erase or a here or here. So for array of I or array of j, so that's why for every operation in my two pointer, it may take at max log n operations. So that's why it is O of n log n time complexity for this one. And coming to the total time complexity, so total time complexity, this would also be O of n log n. Why? Because we know, as it is given in the question, that there is a bound over sum of n overall test cases. So I don't have to incorporate the t while calculating the total time complexity. And total space complexity would be O of n, because I'm just creating a vector and a set, and both have a linear space complexity. So my space complexity would be O of n. So I hope you have understood the implementation. And for the ending remarks, I would like to say that this problem incorporated not only two pointers, but also a nice way to store the minimum and the maximum value while moving two pointers using a set. So that is always a great question to solve, which incorporates a lot of topics together. And at last, I hope you like the problem. Thank you.